Hello, and welcome to your first, real version of online, though you hopefully have been watching our problem sessions. We are going to be running in this format for as long as we need. I'm here almost alone in Hayden. My colleagues are here as well, and the people cleaning all the doorknobs and desks, so know that your dollars are still hard at work. Today we're going to talk about Chapter 6. We're going to continue our discussion of energy. Today we're going to speak more on chemical reactions and talk a little bit about some of the, you could call it mechanics of energy. So talking about pressure and enthalpy and some things like that. So if you have any questions, just raise your hand and then either leave a comment below or send me an email. Otherwise, pretty sure you got my email regarding some of the changes we're making in the presentation of an online course. And know that all the Gen Chem profs are going to meet probably in the next couple days and figure out solutions to exams, for example, and also try to make sure that everything's done in the same way. So if you have any comments or suggestions, feel free to shoot us an email and I'll forward those around. Otherwise, hope you guys are doing well, washing your hands, and enjoying your time off. I'm going to guess you still have work to do. I know you have a homework due today, Wednesday, even though this is being filmed. It is Tuesday, right? Yeah. And so let's do it. I'm also going to put a new homework up online, and that'll be due not in 1 week, but in 2 weeks because of the break. So don't forget to enjoy your break if you've forgotten that you have one coming up. So today we're going to talk about not just energy as a concept, but specifically the energy of chemical reactions, right? Generally, we look at things like reagents first and talk about chemicals themselves, and then we talk about their transformations or reactions. That's pretty much all of science and engineering in a nutshell. And so let's start by taking a theoretical molecule, which could be made up of two different elements, here just labeled A and B. And we're going to imagine that we go through some reaction and we break it down into A and B separately. And so the first thing we're going to just mention is, again, not talking about mechanical energy at the moment, though that is the focus of our lecture today. Instead, we are going to talk about, I just want to make sure it's recording. Okay, it's recording. What we call chemical energy, which is the energy stored in those bonds, and the change of these bonds is going to elicit changes in mechanical energy as well. But for the moment, when we think about this reaction, we are thinking about what we call potential chemical energy. And so here what we're thinking about is the energy, again, stored in that bond. And so one of the things that I have never forgotten from when I took chemistry back in high school was whether or not forming bonds releases or takes an energy. I know biologists like to think a certain way, but here in chemistry we like to think that the formation of bonds, or things coming together, so the reverse of what we have drawn here, is actually going to release energy. And the way that I like to remember this is that when things come together, you can hear some noise or sound energy there. That's going to be a reminder that things coming together is going to release energy. And generally, it's going to take energy to pull things apart. So in the reaction we have up top, to separate A and B, which were bonded, we're going to put energy in and come out with A plus B. Now, depending on the reaction, we'll see in a moment how that may be somewhat different, but for the most part, forming bonds is going to store potential chemical energy as we have here. And so now let us distinguish between whether heat, which is different than this chemical energy, is coming in or out of a reaction. And we gave some examples last class of, say, combustion, for example, releasing heat, right? A lot of fire and light. Whereas you might say have an ice pack or a cold pack, if you crack it and break it, it will become cooler over time. And so two different ways that heat can come in and out, and yet the bonds that are forming or breaking are going to be related to chemical energy, which again is distinct. So we're going to talk about what we call exothermic reactions. And we're also going to look at what we call endothermic reactions. And so in this case, exothermic reactions are going to release heat. We're going to think about combustion again. Did not leave myself enough room there. We're going to think about fire. So essentially heat coming out of the system. And then the endothermic reactions here, we're going to be thinking about things like, for example, making sugar, which I'll describe in just a moment. And we're going to think about heat going in. And the way that I always remember this is that endothermic sounds like in just a little bit. And so you can think of endothermic as heat coming into our system versus the exothermic ended coming out. And so looking at an exothermic reaction, there's one that you guys have seen before in many different formats, right? We have our combustion of methane. And we can think about the products here as well. And you may be balancing along with me. We know we need, right, an extra pair of hydrogens and also an extra oxygen there as well. So this is going to be clearly exothermic, right? Here this is combustion. This is burning methane like when you turn on the burner on your stove. In comparison, we can look at an endothermic reaction, what it takes heat to do. And so in this case, we can think about a reverse reaction, sort of like reverse combustion. In this case, we're going to take both carbon dioxide and water. And this is where I would generally pause and ask anybody if they know where we're going with this. This is going to be that reaction we see in biology, which is why biologists sometimes think about energy a little bit differently. We're also going to take light, in this case sunlight, and so here we just have a chemical representation of a plant making sugar. So here we again have glucose. And then also, right, that extra oxygen. We know that plants put out oxygen and we breathe in our carbon dioxide. Right, so essentially potential chemical energy can either be released. Well, I guess it's going to be stored when we form bonds. You can see here we're forming more bonds, we're breaking more bonds up here. And so in this latter example, we're going to be storing that chemical energy and we're going to essentially be putting in heat to help that happen. Okay, so I get to do this, which I so wish I could do in class. And we're going to move forward. Let's talk just briefly about that AB reaction before. So we have what we in chemistry refer to as bond strength. Wow, I can never spell, but today is not a good day for me. We all have a lot on our minds. What we're going to think about here is the strength of that bond between two atoms is going to be related to essentially how much energy it takes to break. And just for right now, we'll get to this in chapter 8 and 9 as well. But essentially, a strong bond, which we will come to define, will essentially take lots of energy to break, which makes sense, right? Just like if you try to break something that's really tough, takes a lot of energy or effort from you. So a strong bond here is going to require lots of energy. RBCQ, UIRE. And we'll come up with some better definitions about bonds in the next chapter as well. 2 chapters, technically. So it's nice that we're talking about all these ideas relating to heat. The question is really, how do we actually measure these things? And so one of the ways that you guys will learn about is what we call calorimetry. And we will use what is known as a calorimeter to essentially measure the amount of calories that are in and out. Meter here referring to, well, I guess a unit, and then metry referring to the study of. And so in this case, right, we're talking about a calorimeter, which is the instrument we use. And so, ooh, there's 2. Wow. We'll see that in a sec. And so let's just draw up an idea of what a calorimeter looks like, how we might measure these, and then we'll explore some of the nuances of how this instrument is used, for example. So the neat thing is that you guys may actually do an experiment one day where this can be done with just a styrofoam cup. The premise here is that you're going to keep all the heat of some reaction in. So if you're going to say test how well different fuels burn, you're going to have some sort of system that's going to trap all of your heat. A styrofoam cup is good enough for an introductory undergraduate lab, but right, they're probably going to come up with really thick insulated walls for the studies that they do. Now inside this, we are going to have it filled with water, not only because water's cheap, and also, as we know, stores energy very well and doesn't change too quickly in temperature, but also, well, I guess those are most of the reasons there. We're going to have, no surprise, a thermometer, which I will try to draw here. right, with our little bulb. And essentially what this will allow us to determine is the change in temperature, right? So we're going to look at our delta T. You can see we're going to be compiling all the components of our Q equals MC delta T from yesterday. We are also going to have in here something like a stir bar. So this is going to be like a little propeller or fan that mixes everything up. And that's just going to allow us to essentially make sure that the heat is evenly distributed. We are then going to have what is affectionately referred to as the bomb. Technically, nothing is exploding. We'll find that nothing changes volume here, but nevertheless, we are going to have combustion, and our bomb refers to this sort of central chamber in which that combustion will occur. And that's usually just generally fixed, so it's staying in one place. Water is allowed to flow freely around it. We are going to have some sort of sample. And this could be anything that you want to test, right? This could be generally something that will combust, something organic, very likely. Could also be, I guess, other things like things that form oxides, like metals. But the premise here is that you're going to know the mass of that sample, right? So you're going to have your M, essentially in kilograms. And so we, knowing, say, the specific heat or the heat capacity of this system, you could determine the actual amount of heat coming out. And so we'll look at that in just a moment. The other thing we're going to find is that you're going to need some stuff to actually combust, right? So you're going to have some O2 in here. You're probably also going to have something like an electrical system to essentially allow for ignition. And so what we'll find is you're going to light it up, you're going to burn what's inside, and you're going to measure the change in temperature of that water while the entire thing burns. And so while you can put chemical samples in here, you're also generally going to put in food. And so the way that they may determine, say, the calories of a new product or even an old product to make sure that it is right, is they're going to put your food inside, they're going to burn it up, and quite literally determine how many calories it is. And the premise there is that it would be the same in your body. Your body is an open system, right? Energy and mass coming in and out, and yet this is a very closed and isolated system, right? Not a lot of energy or heat coming within and out of these walls. And so what we're going to find in this case, right, no surprise, is that we are at constant volume. And so in this case, we can say that the change in energy of the system is going to be related only to the heat at constant volume. That's what that little V is going to mean here today. And so this is going to be a very specific system. In reality, we actually work in the opposite. We are not at constant volume, right? Gases can expand and contract at any point, generally. We are at constant pressure, right? The pressure in the room is going to be the same or be intensive, as we'll find. And so essentially what we're going to be measuring here is what we call the heat of combustion. And so from, say, the heat of combustion, the mass, and the delta T, you could come out with, say, for example, your C, right? And so in this case, let me try to do this in my head as we go. You'd have the Q, you would have it over the M and the delta T. This is just a different version of what we saw the other day. That's totally not how we do it. MC delta T. Right, and so you could determine the specific heat or even the heat capacity of a given species, and that's how we actually do this as well. So let's actually table this for just a second. Oh my God, that's so nice. And we're going to bring this idea back in just a moment. We're going to talk again about constant pressure versus constant volume. But let's look at my favorite thing to look at. Let's look at some units. So in this case, let's look at what happens if the volume changes. It's like so quiet in here compared to when all of you guys are in my class. It's really sad. I may try to stream something on Twitch. I did figure out how to do it the other day. So if you really like that, you can watch me stream a class, and then I'll play some Animal Crossing for you after that's released. Okay, so let's start actually by looking at energy. And we're going to begin to relate it to volume. So in this case, we're going to imagine that volume times something is going to be equal to energy. You might not know at first that that is the case, but we're going to work up to see what that is. And we're going to determine this using the units that we're most familiar with. So energy, as we know, is going to be measured in the joule. We also know from the other day, right, that it is what we call a derived unit. It's made of lots of little pieces of the other base units that we're looking at. Volume, you may well remember, is comprised of the length, the width, and the depth, or the height, but essentially three measures of length. And so the units for volume here are going to be cubic meters, or meters cubed. And so a good thing to do right now would be to pause the video and try to determine what times meters cubed gives you this here. And so I will let you freeze right there. And then let's see how we can come up with that. So one way to do this would be to take the joule and divide it by meters cubed. So let's see, let's do some dimensional analysis. Sounds fancy, really is not. And then we're going to take it over meters cubed. That is going to be the same as having this, right? We could also think of as over 1, and we're going to flip it. So in this case, we're going to have 1 over meters cubed. And I think I'm still on the board here, not much longer. We see that we can get out kilogram over meter second squared. And good, I just did it. So these are the units of whatever it is that this represents. And these probably don't look like much to you, at least just yet. But let's see if we can get to this another way and determine first what it represents, and then also whether it's extensive or intensive. We'll see that's going to be relevant in just a moment. So what we will find is that these units that we've just come up with, which I am botching right now, ms squared, are going to be the same thing as if we take a force and apply it over an area. And the way that I always think about this property that we're coming out with is to think of someone wearing high heels, right? It comes down to a very thin point, maybe like a stiletto heel, and so there's a lot of force, if it's a very large person, in this stiletto heel, across a very small area, right? And so in this case, we can think of that as pressure. And so what we'll find is that energy in joules can be calculated from the volume of a system and also the pressure that the system is acting under. And we can see this with force as well. If you're thinking back to Physics 1, force is essentially a mass times acceleration. We have the mass, we have times the acceleration, and then if we put that over meters squared, you can double check to see that we actually get out these same units. And so generally, just to talk about these for 1 second, the units of pressure are going to be something like the bar or the atmosphere. These are going to be the units that you hear about when you discuss weather. But technically, the SI units, I'm not sure if the SI units are actually this. It may be the Pascal, but they're going to be essentially the same idea. And so let's just take a moment to look at, say, energy, which we know to be extensive, and volume, which is just a base measure, right? If you double your system, your volume would double. Yeah. And so in this case, we can work towards the idea that the pressure is actually intensive. And the way I like to remember this is think of a balloon, right? The pressure inside that balloon is the same at any point. Similarly, the pressure in this room or in the room you're in is the same in any corner. If it's not, you have wind. And so in this case, we can think of it as the same throughout, and it doesn't depend on the size of the room, right? If I take a portion of gas in my hand over here versus over here or over here, pressure's still the same. Sadly, I don't think I have another board to go through, so let's pull this first one down. And let me erase. Oh, I forgot my nice eraser. I was going to bring it for the lecture today. But these boards are so much nicer. We have the really sad boards downstairs. Okay. How is this online lecture going for you so far? Very nice. Okay, so now let's go back to our original definition of energy. Try to remember what that is as I write. Energy we are thinking about as the ability to do work. And the first time I brought that up, you probably thought of work as what you're doing right now, right? Taking notes, listening actively, pausing the video and doing your problems. But we're going to begin to think about a more scientific definition of work in just a moment. So know that it was really a trap, right? You thought that this was sort of a colloquial version of work, right? What you do when you do your part-time job or whatever it may be. But we actually have something else that we're referring to when we talk about work. So I'd like you to imagine for just a moment that you have a spaceship. That came out really well. And I'd like you to imagine that the fuel inside the ship is actually just made of, say, a soda, right? So gas dissolved in some sort of liquid. And the way to get this rocket to go is you're just going to shake it up and it's going to fly up. And so a couple of things you will find, right, is that the pressure inside this will build up. And so in this case, we will have pressure changes, right? We will also have volume changes, right? The volume of this system will increase as it shoots the gas out. The gas will expand. And so the pressure volume changes are going to create what we call pressure volume work. And so again, work here just means that there's some sort of mechanics going on. And specifically, work here will not refer to changes in heat. It will refer only to changes in pressure and volume. And so in this case, we will define work with W as the negative pressure and then change in volume. Right? We're going to imagine that the pressure is relatively constant in this room, in this example, and yet the volumes are going to change, right? Even though the pressure would build up, it will release as this shoots up over time. And so in this case, we have the pressure, which is constant, times the change in the volume. And if you've ever spilled soda on yourself after shaking it up, it's because of this change in volume that happened, right? It expanded from the size of your bottle outwards onto your pants, wherever it may be. Something you probably noticed was this negative sign that is up here. Scientists use this to denote that you're losing energy. So in this case, our negative sign shows that we're losing energy. You can probably also guess that for exothermic reactions, where energy is coming out of a system, it could be considered to be negative in these examples. And so we've reached actually a really neat moment in this course where we're going to begin to talk about one of the laws of thermodynamics. The good news is you've actually already seen it before in a slightly different way. The bad news is that you have whole courses related to it in engineering and science, and so you are far from done with it after I introduce it. And so let's talk just briefly about our first law of thermodynamics, which I will just call the first law of thermo right now. The neat thing is that it is actually just the law of conservation of energy. So nothing too new, something you probably had heard about before. And right, the whole premise here is that if it's the law of conservation of energy, and I want to make sure that these are still 50 minutes, which we're doing well with. What essentially we're describing here is that energy is neither created nor is it destroyed. And so again, if you're a fan of Full Metal Alchemist, this is pretty much the same principle as the conservation of mass or charge. Here we're just talking about energy. And this is only for a closed or isolated system, right? You could, in theory, have energy coming in and out of an open system like your body. And so, right, we described the other day the idea that the energy out minus the energy in of, say, a change in process, burning something, some chemical reaction, the total is going to equal the delta energy, right? That's how we represent the change in this case. And we will now define this as the sum of the heat plus the work. So right here we have all of those changes related eventually to temperature, and then also everything related in this case to changes in pressure and volume. And so you can see, right, that in this case we're going to be balancing all of these different components. And something we will find is that this delta E is what we know as the internal energy change. Which in this case is going to refer to that energy within the system and any changes that may happen. Some of what was work may contribute to heat with, like, say, friction, right? Mechanical motion changing into heat, or the other way around, right? Enough heat, and you might, say, move away from the stove, for example. That could be the work that comes from that heat. A horrible example, but you get the idea. Something else that we find is that this internal energy change is what we call a state function. And the premise here is that it has nothing to do with how it got there, it only matters where it is. And so I would argue that if you know you're going to be late to my class, I only care that you are in my class in a certain state, say in a certain seat. And it doesn't matter if you sprinted up around the park or the trains or took an Uber, whatever you need to do to get there. When it comes to attendance, attendance is just a state function. It only matters that you are in a specific state or place, not what we will determine to be a path function. Okay, and let's actually see an example of this. Let me try to save that calorimeter for just a minute. Okay, so let's look at the difference again between heat and work and show how it doesn't matter how you get to where you're going, the state of the internal energy is going to be most important here. So I'd like you to imagine that you have a battery. You guys probably don't use batteries quite as much as I did when I was a kid. My Game Boy would not run unless I had a bunch of Duracells. And we're going to imagine that to start, your battery is fully charged. And so in this example, we're going to imagine two different ways to get to essentially an uncharged battery, or what we call a dead battery. And we're going to do one route where we're going to look at this at changes in heat. And we'll do another route where we're going to look at changes in work, relating to pressure and volume here, right? And so in this case, right, we're still going to use our battery in each example. We're trying to uncharge it. And so let me draw the battery for each. And I guess I'll draw sort of a neutral face because it's being uncharged or dying. And so, right, we know that we're going to end up in either situation down in this quote-unquote dead state. But in the first example, we're just going to take a paper clip, which is going to act like a resistor. And so if you've never done this before, please don't hurt yourself. But this is going to warm up, right? You're going to feel quite a lot of heat. And so over time, you will release heat. And essentially, once all of that electricity is passed through and the battery is dead, you will be at a different state. And so we'll see that in just a moment. Alternatively, you could say hook this up to a little fan. And that could whir and essentially do what we call mechanical work. And so you could see two different routes to the same state, right? A charged state and a dead state. In this case, the delta energy, or the change in energy, is the same, right? Full, empty. So the delta E is the same for both. And it doesn't matter which route you took. The premise here is that you are at the same state in the end. The delta E is the same. And now you're going to need to either recharge your battery or buy a new one. Okay, here we go. Let's look at an example using calorimetry. So in this case, what I would like you to imagine is that we're going to determine the amount of calories in a gram of olive oil. So we'll use the equation that I just erased. I'll write it again. And so the premise here is that in this example, I'm going to put just 1 gram of olive oil in there. So now we have our mass. What else? We also know that olive oil, well, we actually don't need that. We know we're going to burn it. Something we'll find is that from the thermometer, the delta T, in this case, is going to go from 22 degrees C to 26.049 degrees C. Always important to put those in the right order. We're thinking of this as the initial, right? The water starts off as relatively cool, and it ends up as a little bit warmer in this example. But there is another thing we're going to need if we're going to determine the Q in this example. So take a second to think about what that might be. Remember for just a moment that Q equals mc delta T. So this is just a slightly fancier version of what we did the other day. And so in this case, we are going to determine that. That's what we're looking for. We have the mass in grams. We have the temperature in degrees Celsius. And so we need, in this case, the specific heat. And we'll think about our units for that as well. In this case, we're going to find that they actually give us the specific heat of the system. They give us the heat capacity of the system. So in this case, our heat capacity is going to be 9.032 kilojoules per degree C. So if you've been following along, you're probably wondering where the grams is here. Something to note, because you buy this system and use it, they actually know how much this weighs, and they factor that in to your specific heat capacity to give you the heat capacity. So essentially, from where we were yesterday with our specific heat capacity, is we just took that and multiplied it by the mass of the calorimeter. Or in this case, I guess, of the water that you would have in your calorimeter. As long as the walls aren't heating up, don't worry so much about that. And so we'll find, right, seems pretty high compared to water even, right? They probably build it that way so that it can absorb all of that energy and not change too much, even though a gram of olive oil isn't all that much to burn. Okay. So the question here that we're going to work out is, once we determine the heat, we're also going to determine the calories, capital C, so that's the same thing as kcal, per gram. And this is exactly what you would expect to see, well, not in these units, but on the back of, say, a bottle of olive oil, right? It would tell you how many calories per serving or gram. You can do those conversions as well. And so, in this case, we have all of our pieces, right? We have our mass, we have our specific heat capacity, and we have our change in temperature. The only thing that changes in this reaction or equation is going to be that Q is just going to equal, sometimes what we do is capital C delta T, and the premise here is that M and C are going to become that capital C. You'll notice that specific here only refers to something, for example, joules per grams degree C. There's a variety of different units we use in engineering and science that are specific. It just means per mass. It means that it's intensive, and you can use it anywhere. This is extensive, refers specifically to this bomb calorimeter that we're using. Okay, let's do it. Trying to think about where I should write. Well, I'll just write up here. Okay, so the first step that you're going to take is to think about the relationship between the energy in your olive oil and your reaction, the combustion that will occur, and the calorimeter itself. So we're going to talk just briefly about the sign here, and I'll try to go through more of that later. In this case, the heat related to the change in the calorimeter is going to be negative, or the opposite of the heat of the reaction. And that makes sense, right? The reaction is going to release heat. We talked about how that is exothermic. When things lose energy, they are negative in our convention. And so thus the calorimeter must take in that heat and gain it. The calorimeter sees it as endothermic, and thus it is positive. And so I'll even add a little positive here. The other thing that will help us is knowing the relationship between joules and calories. Notice that we were given the heat capacity in kilojoules, and yet we want it in calories. And so take a second to remember that 1 capital C calorie is going to be equal to 4.184. And careful here, right? These are 10 to the 3 small calories. So similarly here we will have 10 to the 3, or kilo, and then joules. And now look just briefly at, say, what we want. We want calories per gram versus, say, kilojoules, which we were given. So the good news is that our calculation isn't so bad. In this case, the third step is going to be that the Q for the calorimeter is going to be equal to just capital C delta T. So in this case, we're going to take our, 9.032. Did I convert it? Not yet. We're going to get there. Kilojoules per degree C. And then we'll do our subtraction, right? Am I about to run off the board? Just a little bit. 26.03049 degrees C minus 22.000 degrees C. Just take a second to type this into whatever you're using to do math with me, because I know you brought your calculator with you. And so we'll find that the Q calorimeter is going to be equal in this case to 36.57 kilojoules. So we're most of the way there. Now what we're going to do is convert these kilojoules to calories, and then we'll take the amount or the grams that we have. So I think it's time we destroy our bomb calorimeter. It was going to happen at some point. And so let's just do a little bit of those conversions that we're used to. The important thing to remember is that Q is equal to a positive number here. And so if we're now working towards the calories related to the olive oil, we're going to be negative. So no surprise, I'm going to start with that given, or that calculated value. In this case, 36.57 kilojoules. Right? That's going to be from the reaction. And we can start off by just dividing it by 1 gram of that olive oil. Right? So now we can see we're slightly closer to the grams of olive oil that we were going to. Last but not least, let's do our conversion. So in this case, right, we'll just take it from what we had. Don't have to worry about kilo here because we're also going to kilo. We can think about it as either 1 calorie or 1 kilocalorie. Notice the capital C here. And so our answer comes out, importantly, as negative, that we know. And the value that I get, well, I should have paused to let you pause, but we can see here as well. And our units are going to be calorie per gram of olive oil. Which seems about right? Around 9 calories per 1 gram, right? That's going to be probably a portion of a spoonful. And so that's why you don't add too much olive oil when you make pasta, to say the least. Okay, so let's just come through one more concept, and then we'll be good for today. Looks like I'm a little early, probably because I didn't have wonderful questions from all of you. So please add them below if there's any confusions or comments. And my guess is that you'll be doing a lot of Q equals MC delta T on this next homework that I'll put up. There's not too much else in this chapter, though the next lecture will cover some of the other things related to energy as well. So I just want to talk about a little bit how we discuss in science changes at constant pressure, which is, again, the reality. We looked at the bomb calorimeter. That was constant volume. Good for science, not so real world, though. So let's talk about constant pressures. And again, the reason we're interested in constant pressure is because we live in a constant pressure setting, right? Well, I guess in reality there are changes in pressure related to wind and whatnot, But when you're doing an experiment, generally you're going to be at a constant pressure, or whatever the pressure in the room is. And so let's start with our definition of that internal energy. We remember that it is the sum of the heat and the work. And so the first thing we're going to do is introduce a concept known as enthalpy, which we will come to find is going to be intensive as well, which is going to be representative of, right, an entire system, no matter what portion you take. And so in this case, enthalpy is going to be H. And we'll start by seeing that in this case, it's going to be equal to the energy, not the delta, just the energy, plus the pressure and the volume. So I'm giving this to you and we'll work through a derivation, but know that in this case, this is just sort of a more real-world example than just using E, at least to start. The first thing we're going to do in this case is look at the change in the enthalpy. So in this case, if we take the change of H, the out minus in, we're also going to look at the out minus in of the energy. And in this case, I could do of each of these, right? In theory, I could do delta P times regular V, no change, and I could do P times delta V. But in this case, what we're going to find is that we are at constant pressure, so there is no change. So in this case, we will come to P delta V. And that's why it's enthalpy, because only the volume is changing. If pressure were changing instead, it would be a different measure, and you don't want to go into that right now. So now let's substitute in things that we know, right? We know that delta E is Q plus W, so this can become Q plus W, and then we can also keep this P delta V. The other thing we may remember from before is that P delta V is going to be negative W, or the work that's the loss of work, I guess you could consider. And so simplifying this, we're going to get essentially, I should have had this there, right? We know we're at constant pressure. We talked about constant volume all the way back. And so we can see the negative W and the W will cancel. And so in this case, QP would be plus W, and then also minus W. We're thinking of that as negative W. And so if both of these cancel, the change in enthalpy is going to be related only to the change in heat at constant pressure. And so in the real world, any change in heat is going to be best described by what we call enthalpy. And we're going to use that next lecture to look at all of these changes in reactions, right? Kind of lied and said this was going to be about lots of reactions. Next class will definitely be about those things. Don't forget, you guys have a homework that is due later today. I'm giving you guys an extra day to submit online because of all the craziness. Send me emails with comments or thoughts. I am on campus if you are still here and very bored. It is a little quiet and sad here right now. Don't forget to continue washing your hands, and I'll see you tomorrow, same time. Not sure if it's the same place, but I do like this board. Have a wonderful day, and I'll talk to you guys soon.